Okay, class. So this is a crazy long homework packet, which is part of why I was a little bit late with it. And also, I was a little bit worried because I had mistakes in my algebra one from before. Um, this is a crazy long packet, but this video is just going to walk you through it. So you actually don't have to do the reading if you follow along with this video. And I think you'll be perfectly fine. So this is for my brother is a roboticist at Arizona State University, and he is a great mechanical engineer, and he's also very dyslexic. So he is a purely auditory learner. And so if you're an auditory learner, welcome. This is for you. So we're going to be talking about Newton's cradle. And the big idea in this big idea homework is the way Newton's cradle works is, it has this funny thing where no matter how many balls you pull back, that's how many balls will come off the end. And it's really fun to watch this. And the reason is because both momentum and energy are conserved. And conservation of energy and, surprisingly, momentum are going to be really important when we get to relativity. Photons having momentum without mass, relativistic mass, it's going to get fun. It's going to get really interesting. But it starts out like Newton's compass. It starts out by these kind of simple things. And the purpose of this homework is to take these things, they'll be a little bit bigger ideas, but we're going to show you how they really are related to the simple stuff. Okay, so the first thing in here, can skip the intro, is that momentum has a mathematical formula, and it's represented by a P, just to kind of keep it separate, and it's the mass of an object times its velocity. Energy, in this case, we're going to talk about two different kinds. We're going to talk about potential energy, which is sometimes represented by a U. Einstein uses this U in his papers. The potential energy you put into something, or the potential energy we will put into something, is the mass of the thing times the acceleration due to gravity. This is a particular kind of potential energy, times the height. So if you are dropped from 3 feet, you have less potential energy than if I drop you from, much higher. Let's hope you have a parachute. And I'm not trying to accelerate you towards the sun like I did last time. The other kind of energy we'll be talking about is kinetic energy, which is 1/2 the mass times the velocity squared. And one of our big objectives in this thing is to show that these two things are both conserved and they're not the same stuff. And that's kind of a difficult concept. It was for a lot of people from the 1600s because they're invisible. And they're both related to mass and velocity, but they are very different things. Okay, so now we're going to go to the pendulum part of the lab. So I'm going to hit pause, and there's another part that will start up where I'm talking about the pendulum lab. And so after that, I'll cut that. I'll make another video that will take you, that next part of this video will take you all the way to momentum in the system. Okay, so I'll hit the next, there'll be another little clip, and that will end the video, and that one video will take you to, putting momentum in the system. Why did that not show up as a spell thing? All right, here we go. Next, onto the pendulum. Hey class, so this is this video is meant to be done along the way with your homework on the Newton's cradle. So in the first part of the Newton's cradle, I talk about a pendulum because essentially the Newton's cradle, if I go over to our Power School Learning, the Newton's cradle is a set of pendulums or pendula, and what we're going to do is we're going to put some energy in. We're going to put some energy into the system by lifting one up, and then we're going to see that energy and momentum being conserved. So the first part of the homework video, oops, I didn't mean to pause on that. The first part of the video, I'm going to talk about the pendulum and what's going on with the energy there. So let's go to that pendulum lab. So I lift my, the first thing I talk about in the homework is that if we have a second one that's lifted higher, its energy, its potential energy is higher than the one that's lower. The height you lift something up has a great deal to do with its potential energy. The second thing is when we look at this, once I have moved, so in this, I'm going to move my pendulum to 45 degrees. And once I move it there, and I press go, we're going to see that energy will be converted into kinetic energy and back again to potential energy, but the total energy will be conserved. Now notice that I have friction set for Earth. Oh, I'm sorry, I have friction set for none. So it's not going to, on Earth, your pendulum would eventually slow down over time, and that's due to friction. But we're not going to have any friction because we want to see what a perfect pendulum would look like. And the gravity is going to be set to Earth. Notice you can play around with it and do different things. Okay, so once I press play, what I want you to notice is the total energy stays the same. It just, when it's down at the bottom, I'll make this go slow. When it's down at the bottom, where it's back to zero, the height is zero, the kinetic, it's all kinetic energy. It's 100% kinetic energy. Then when its height goes up, as its height goes up, it gets all the way back to the maximum it'll be, and it gets all the way back to 100% potential energy. So the energy in this bob, the total stays the same. It just converts from one form to the other. Okay. It is one kind of fun thing. If we remember, just an aside, we remember a body in motion tends to stay in motion unless acted upon by an outside force. The outside force here is gravity. So if I move this all the way to none, it's showing kinetic energy because it's stopped the simulation. But if I move it all the way up here and I move gravity to none, so there's no force acting on it, it just stays where it is. The simulation's running, there's no energy in it, it just stays where it is. If I go back to Earth and I start it moving, I can make it move in normal speed. If I start it moving in normal speed and then suddenly while it's moving, I change gravity to, it's just going to go forever, and the only thing active upon it is the string that's holding it together. So that's kind of fun. A body in motion tends to stay in motion unless acted upon by an outside force. Okay, back to the main lab. I'll come back to this recording when I get to the next part in the homework.